Okay, so I have a guest lecturer with me right now. Um, my wife Heather and I presented at the TecBridge Innovation Conference back in August 2019, and we talked about our two joint patents we have, the adjustable wheelchair and the pressure redistribution system. And here's what they look like. So these were senior projects that we built and designed with the students, and we've partnered with the students, and we were awarded U.S. patents on both of these systems. So we're going to kind of talk about um, how each one of them works, the inspiration behind them, and how they can be used in society to make people's lives better. So my wife Heather is actually the one that came up with both of these ideas. She's been working as a licensed occupational therapist for several years, and she saw a need that the patients can need. And we're going to talk about the intricacies of both designs, but there was a need for both of them. And myself, working as a professor in the mechanical engineering department, I had a team of eager students that wanted to get involved in the project, and it was just a great collaboration. We were able to work together and brainstorm different ideas, and then build the prototype, and then create our own partnership after they graduated. We worked with patent lawyer to actually pursue the patents, and now we own them, and we're trying to license them to companies. All right, so the first one we're going to talk about is the adjustable wheelchair. And the objective is that it can easily adjust and grow with the patients.
So, where did this idea come from? Well, it came when I first graduated. I was working in a 4-story skilled nursing facility, and I had to go to the basement to get a wheelchair for a patient because their chair no longer fit them. And when I was down there, the elevator broke. So I had to carry a 50-pound wheelchair up 4 flights of stairs to the patient. And while I was doing that, I thought, wouldn't it be easier just to get a chair that fit the patient, that could expand with the patient? So a little bit more background. I'm working in a skilled nursing facility. It's actually considered what they call a CCRC, which has skilled nursing, personal care, and independent living. It's a tri-care building, which unfortunately no longer exists. And so that's where this idea came from. But going back a little further, what about patients living in their own homes? So Medicare or Medicaid, Medicare is federally funded, Medicaid is funded by the state. They say patients are entitled to one mobility device. So that's anything from a single point cane, basically a stick with a handle, to an electric wheelchair every 5 years. So let me ask you, 5 years ago, do you look the same today as you did then? Or think about a 5-year-old versus a 10-year-old. Much different. Still one mobility device. So we also needed something that was simple for people to use. Not everybody has a master's degree like I did. We needed something for your average grandma to be able to put grandpa in. And not all standard sized wheelchairs fit every person. There is no such thing as a standard sized person. So standardized wheelchairs come in increments of 2 inches, 14, 16, 18, 22. They're the most common. So facilities have to stock each of these sizes. I can tell you in my facility, we have 18 through 22 only, because the smaller ones, they'd rather us pad the chair than buy a smaller wheelchair. It's more economically feasible for them. And wheelchairs don't grow with the patient. If a patient gains or loses weight, which frequently happens in the frail elderly, or, like I said, think about a 5-year-old versus a 10-year-old, the chair's not going to grow with them. So this is what I'm faced with. I need a chair that grows or shrinks with my patient. So what are the basic classifications of a wheelchair? Pediatric, obviously for kids. Average, which would be the 16 to 18 range. Or bariatric, anything over 20 inches. So what are the basic elements of a wheelchair? They're collapsible. An average wheelchair is a 18 by 16 wheelchair. Needs to support somebody with a weight of 200 to 300 pounds, and needs to weigh between 40 and 50 pounds. Like I said, I was carrying a 50-pound wheelchair up 4 flights of stairs, and that's without the leg rest. So what were the design requirements that I proposed to the students? It needed to be safe for the person sitting in it and the person putting them in it. The wheelchair needed to go from 14 inches to 22 inches because that's the average range that I could fit the average person in. The seat must adjust the width of the chair with the width of the chair. Wheelchairs should not exceed more than 50 pounds. Anything more than that, and grandma's not fitting it in her trunk. The wheelbase cannot exceed 36 inches. Why, you might ask? Because according to the Americans with Disability Act of 1992, all public buildings need to accommodate a wheelchair, and they figured the average wheelchair can fit through a 36-inch door. So anything built after 1992 meets this requirement. It needs to collapse to the same width as a standard wheelchair, about 12 inches. Easier to store. And it must hold patients weighing up to 300 pounds. This may seem like a lot, but if you consider that a lot of people also have braces or something like that, it's really not.
Okay, so before you look into creating a design, or especially if you want to pursue a patent, you need to do background research on what's called the prior art. So this is to ensure that the new invention is novel and new, that you're not just trying to patent somebody else's idea. That's basically plagiarism, right? So this main unique feature of our invention when compared to other adjustable wheelchairs is this continuous adjustability. So you're going to see on a couple of these pictures that there's adjustment braces where you could pull a pin and it'll adjust into the, like, say, the discrete sizes that Heather was mentioning, that it could go to 20, 18, 16. But what if you need a continuous adjustment? What if you need 17 inches or 16 and 3/4 or, any other size in between? So we wanted a design that could be continually adjustable and completely match the patient for maximum comfort. So that was, and we were never, from all our prior art research, from ourselves, our students, even our patent lawyer and his team, we couldn't find another adjustable wheelchair that had that feature. So that was definitely a novel aspect of ours and something that we claimed on our patent. Another feature was the ability to collapse and return to the last adjustment setting. Like Heather mentioned, very frequently, someone would use the wheelchair in their house, but then they would have to go somewhere with it. So it would have to collapse, fit in a trunk, and then re-engage at the last position. You wouldn't want something that would have to slowly adjust down to the 12-inch width and then take a long time to adjust back. The patient would want to be able to just quickly engage it back into the width that they last had it at. So some of these other patents that we saw, they were able to collapse down, but they took quite a long time to go back to where they were previously. And even that, you'd have to fine tune it to get it right back. So we wanted a system that could just go easily exactly back to where the last setting was. All right, so here's just a couple snapshots of the CAD design. So this is part of the design process before actually building something in the real world, well, let's draw it in computer land and let's see how it looks and we can see how things work out. So we were basically using a standard wheelchair, the wheels and the base. And the thing we replaced was the frame that connected the two wheels together. So this was kind of what we redesigned. So this is showing on the left this diamond shaped adjustment, and there's a handle that'll adjust through a screw. That's what actually does the adjustment. And then you could pull a pin and collapse it, and that's how it could go back. The middle drawing, this was actually after several iterations of the design. The first prototype we had, we found that the wheels actually kind of wobbled side to side, and they didn't stay parallel with each other, which would be bad. So we had to redesign the gear system, the locks between them. So that little tiny adjustment there that you see, that gear system, that's what keeps the wheels from wobbling side to side. And then the third picture you see is the mechanism to adjust the seat backing. So it kind of works like a seatbelt ratchet system. So the fabric's going to adjust with the chair. And here's a nice comparison of the physical build that matches the CAD model. Okay, again, the gear teeth, that kept the symmetry and movement. So this was probably version 2, version 3 of the design. So, that's very common in engineering too, that you're not going to get it right the first time. I don't know of any design that someone had an idea in their head and drew it and built it, and poof, the very first time it worked perfectly without any adjustment, any tweaking. It just doesn't happen. You're going to have an idea in mind and you're going to try it, and you're going to find that parts of it work, parts of it don't work, and it's okay to kind of go back and redesign it, try it again. So again, this is probably second, third iteration to finally figure out a way to make it so that it was a stable design and it didn't wobble back and forth. Here's just kind of a view on the second slide, on the second page, with the fabrication process. Okay, so how does the core of this design work? How are we able to adjust it and collapse it, make it go back? It all stems from this turning the lead screw with this handle. The handle will pop on and off with a quick disconnect, and you can turn it for fine adjustment. And getting the pitch right was also crucial. That you didn't want to take it too long to make it go to the proper width, but if having too coarse of an adjustment, you would miss the size that you needed. So we found a lead screw that was just the right, where you could adjust it right to where you need it to be, and then it would be locked in that position, so it wouldn't move if you didn't want it to. If you pulled the pin, then the whole system would collapse, and you could store it in the car for transportation, like Heather was mentioning. And then when you got to your destination, take it out, pop it back into place, and pop the pin in. So there's kind of a lot going on right in there that makes this whole thing work. And that took quite a while to figure out how to make this continuous adjustment and collapsibility. You're also going to see the way we designed this, a couple iterations. First, we had maybe an I-beam or C-channel, and then we just came up with the two-bar linkage here. So that was part of the iteration process to try to make it lightweight. You want to stay within the requirements of your customer. So if we said at the beginning of this project, it needs to be under 50 pounds, it needs to be under 50 pounds. So if we made it too heavy, too bulky, it wouldn't be easy to transport. So you can see how this was made out of an aluminum framing for to be lightweight and strong, and also the design of the tubes. You want to make them thick enough so that they don't break or warp, but you need to make them thin enough to consider weight. So it turns out that having the adjustable frame was sort of the easy part of this whole job. Trying to make the fabric on the seat adjust with the frame, that was a much harder part. So one of the members of our team actually came up with a brilliant idea of using a ratcheting system from a seatbelt. So this seatbelt mechanism kind of has this coil spring, so it allows the seatbelt to retract, but then when the ratchet and pawl system will engage, it keeps it from going back in. So the same thing here. We came up with a system to incorporate a ratchet and pawl system where you would disengage the fabric while you were adjusting the seat, and then re-engage it when you wanted the fabric of the seat back locked in its proper position. So basically the driving mechanism is the physical diamond shaped frame on the bottom, and then the seat just goes with it. The seat fabric just goes with it. And there's just another view of the ratchet and pawl system. So here's the gear teeth, and then here's the engagement mechanism that we designed. I love the transitions here. So here's just a couple pictures of the manufacturing process. So you're going to see Justin on the right. He's doing some welding and some machine shop work. Murph on the bottom. He's doing some grinding, but he's also doing some sewing. So engineers, we love to get hands on and make it happen one way or another, even if it means bringing out a sewing machine. All right, so and here's just a picture of working with our students, and overall it really was an enjoyable experience. Heather, myself, students were all co-inventors and equal partners. So we're actively trying to sell the product, and if it ever does sell to a wheelchair company, we're going to split the profits equally. We paid for the patent on our own, so we own all the rights to it. And it was such a proud moment where we were successfully awarded U.S. patent number 9,655,794. So, it's all the patents issued ever in the U.S. government. So it's very proud that we have our patents hanging up in our dining room, and we see them every day. So it's a very proud accomplishment we have. And here's kind of our marketing spiel. We show the varied chair. Maybe the name could change, but for now it's trademark. The only wheelchair that easily adjusts from 14 inches to 22 inches. Continuous adjustment capabilities for maximum patient comfort. Folding does not affect the width settings. It goes right back to where it was prior to folding it up. And it's approximately the same weight as your standard wheelchair for easy portability.
So we continued our collaboration with another group of students, and this was for a pressure redistribution system. So a little bit behind this, we have a lot of patients who ends up with bed sores. Not just from beds. It could be from a chair. It could be whatever they're sitting on. So that's where this came from. I wanted to prevent those bed sores. So pressure sores affect 2.5 million patients every year and cause 60,000 deaths a year. A pressure sore can incur a cost of $9 to $11 billion a year for our medical system. Our objective was to create a system that will sense the patient's pressure areas and quantity of the pressure, alert an external user, so a nurse, a caregiver, of where the pressure areas are. And if the patient is not moved, to redistribute the pressure area to prevent the pressure ulcer. So the end result would be to reduce the number of residents affected by pressure sores each year and reduce the cost to the patient, healthcare facility, and insurance companies, and ultimately save lives. So what's a pressure ulcer? It's starts out as a reddened area that would be considered as stage one, uh, and then it goes up from there to where it actually starts tunneling through the layers of your skin and soft tissue, and sometimes it ends up going into the bone.
All right, so how did this particular system work? So the previous project was a purely mechanical system with only mechanical engineering students. This project was half mechanical engineering students, half electrical engineering students. So we call it an electromechanical system. So it started out with having 4 load cells mounted to this 1/8 inch aluminum plate. There was a second aluminum plate pinned to the first to act as the seat. And then obviously we can have a cushion on top of it, for comfort. And these 4 load cells created 4 quadrants. So we were basically trying to see which quadrant had the highest force at any given moment in time. And if that same quadrant, and we had a timer system in play, so that if that same quadrant had the force too long, then the LED lights would blink and start to display higher pressure region and alert the caregiver or someone else, as Heather mentions, just sort of an alarm system like, hey, it's time to change the patient's position. If nobody came to help the patient, or someone didn't see the alarm, or the patient was left alone, then a manually controlled air bladder would inflate. So then we had a pump basically that would physically shift the patient. So this system is basically geared for someone that can't move themselves around. Even kind of sitting here watching this video, you've probably shifted your weight a few times already just on your own. You're like, okay, this is starting to get uncomfortable. I need to shift from my left side to my right side, or a little to the front, a little to the back. This system is basically set up for someone that can't physically do that on their own. They need help. So that's why this is a much needed system. So how do our warning lights work? Well, first, normal condition, it's always going to just display 3 green, 1 yellow. That's just showing where is the highest pressure at any given time of our 4 quadrants. So it's always just going to calculate the force at each quadrant and just, hey, the highest one gets a yellow. So really that doesn't mean anything bad. It's just that's where the high pressure is at that particular moment in time. Where it starts blinking then, blinking yellow, is it gives you a warning. And this could be easily programmed in the system. So we can say the blinking occurs after 5 minutes, after 10 minutes, 20 minutes, however long we deem is necessary. And if someone's kind of walking by and they see a blinking light, they may want to reposition the patient. Now, then if our time limit is exceeded, now that's when it turns to red. So if the patient is still not shifted to a different position, that's when the air bladder is going to inflate to automatically move him or her. Here's just showing a nice CAD model, how pretty much all the electronics and the inflation system is something that can be housed on the back of the chair in this box here. And then it connects through the hoses to the bladders that would be under the chair. So once again, this would be something, this system could go to a standard wheelchair, or even a stationary chair for that matter. So when we set this up as a patent, we were sure not to constrain ourselves to just a wheelchair. That's why, early versions of this project were called the Pressure Redistribution Wheelchair, but the final version that we got awarded the patent was then called the Pressure Redistribution System. So it could go on a wheelchair, it could go on a chair, it could go on a variety of places. And here's just showing kind of a close-up of the inflation system, where it's going to detect the high pressure quadrant, inflate the quadrant, deflate the quadrant opposite. So when we put air into one bladder, we need to remove air from another bladder to physically cause the patient's center of gravity to rock from one side to another side, forward to backwards. The process continues until the high pressure quadrant is changed. So that's where the control system comes into play, that it's monitoring the high pressure quadrant, and it's going to tell the compressor to run until now the quadrant is shifted to a different position. And then it's going to cut the air off and start the counter again. All right, so for this one, we were successfully awarded a U.S. patent, 10,251,798. So almost a million patents have passed since we were awarded our first patent. We've been working with the Alan P. Kirby Center for Free Enterprise and Entrepreneurship to sell both inventions. We've been working with different marketing agencies. All of us have our own full-time jobs and careers, so we're really not in the business to make wheelchairs. But our goal really is to license this to a capable wheelchair company, and not only for the money aspect, but to really help people. Engineers help people and try and make people's lives better. And we really do think that both of these inventions could help people save lives, save costs to the medical system in general. So our goal is to see these get out there, and that would be great if they could get out there for the world to use. And we look forward to creating new inventions in the future. And here's some acknowledgments. We'd like to acknowledge both teams of former students that are our co-inventors, partners for the adjustable wheelchair. We had Tyler, Ryan, Justin, Mark for the Pressure Redistribution System, Matt, Rob, Amal, Jason, and Autumn. Thank you again to Wilkes Kirby Center, Jerry and Rodney. Many thanks to our patent lawyer, Larry, and special thanks to Don Webster for this particular conference invitation.